So, as you're probably aware, there is a homework that is due tomorrow. Then I can post the solution on Wednesday. That way you'll have time to review it before the exam, which is on Thursday. So you will be allowed crib sheets. You can bring 2 pages, 2-sided. What I recommend is you use 1 page for exam 1, and then you bring that and a 2nd page with you for exam 2. So you can play that to your advantage. You don't have to redo the crib sheet for exam 2. So if you have any questions, please let me know. Come by office hours. Yeah. I'm okay with typing. Yeah. Do the practice exam, and you can tell yourself how hard it is. All right. So that's my biggest suggestion is do the practice exam beforehand. Get a feel for how that went for you. And that might give you a good indication of how the actual exam might go. So, because we got cut off a little bit last time, we're going to finish up the arm Jacobian by doing an example arm. And then we're going to do some interactive review slides using something called Slido. So if you're not familiar with it, it's basically something that you can log into on your web browser, and it connects with the slides so that you can answer questions in real time. So we'll get into that after we do our Jacobian. So the idea was that we have our spatial velocity of our end effector of the end of the arm, where this omega is your angular, v is your linear. So this would be related to your ROT and POT, the change in that. And what we found is that there is a Jacobian matrix which relates these end effector velocities with our joint velocities. And this matrix is our arm Jacobian matrix. And you notice that we write it as a function of Q. So depending on the configuration of our arm, this matrix will change. And we found that this J, if we take it being the Jacobian of the end effector, we'll use a T frame. And this bar just means it's the coordinate-free version. What we found is the relationship looks like this. And I'll note that this is for revolute joints. And we have H2 cross P2T, so on and so forth, up to HN cross PNT. Right. So this is the form of our Jacobian matrix for an arm which is composed of revolute joints. And now if I take this and I represent it in a frame, what would that look like? Well, H1 in the base frame is our H1 representation. And our cross product, P1T, right? So P1T is represented in the 1 frame. So we need to convert that to the base frame so that we can do the cross product in consistent frames. Our H2 we define relative to the 2 frame, right? And so this is the same for the 1 frame. And so we need to represent it back in the 1 frame because this R12 would just be the rotation around H2, right? And how we talked about if you do a rotation around an axis, which is the same as the vector, that it just disappears. And that's why we don't have an RO2 here. And so Then we represent our H2 in a frame, and we represent P2T in a frame. Right, so on and so forth, up to RO n-1 HN. And we have RO n-1 HN crossed with RON PNT. So this is the form that we're going to see, and what's going to change with different arms is how many joints that we have and what these rotation representations are, what these PITs are, and what those HIs are. But the form is going to be the same. So if we look at a 3-joint example, okay, so let's make this my T frame. This is my O frame. And let's say our Z axis and our X and our axes of rotation, H1, H2, and H3. So since all of these axes intersect, I'll put my origin here for 1, 2, and 3 all in the same spot. So doing our product of exponentials forward kinematics, we find our H1. Right, so H1 is in the Z direction, it's just EZ. H2 is pointed in the X direction, and H3 is pointed in the Z direction. And let's say that this distance is 1, and we'll say that this distance is also 1. Then what do I have? PO1 is this distance 1 along the Z direction. And RO1 is the rotation. H1 is EZ of Q1. P12, well, the way we defined it, these are the same point, so this is just 0. R12, we're doing a rotation about H2 of Q2. P23, once again, we're in the same spot. R23 is a rotation H3 of Q3. P3T, we're going a distance of 1 along EZ. And R3T, I'll say we'll keep our axes in the same direction. So this is just identity. So now we want to get the Jacobian matrix for this arm. So if we look at our form, so we have JT H1, H1 cross P1T, H2, H2 cross P2T, and H3 cross P3T. Right. So the form stayed the same because we have all revolute joints, and we have 3 columns because we have 3 joints. So now, let's say I want to represent this in the base frame. That's usually a pretty common one that we do, but it is possible that maybe you want to know what it is relative to another point, in which case you could do that as well. So we represent H1 in the base frame, H1 cross RO1 P1T, RO1 H2, RO1 H2 cross RO2 P2T, and finally RO2 H3 P3T. So we already have a good portion of this. We have our HIs and we have our RI minus 1I. So the last thing that we need are these PITs. Well, P1T would be P12 plus R12 P23 plus R13 P3T. Right? So we're just going from 1 to T, and we're going by each joint. Right? So if we look back at our equations here, this one actually works out pretty nice for us because P12 is 0, P23 is 0. So it turns out this is just R13 P3T. And we have P2T. We have P23 plus R23 P3T. Right? So once again, now instead of going from point 1 up to T, we're going point 2 up to T. And we're representing everything in the 2 frame. Right? So this worked out nice for us again because P23 is just 0. And then P3T, if we look at our figure up here, so we're going from 3 to T, so you can see that's a distance of 1 along EZ. Right, so what is R13? Well, that's R12, R23, and now we have P3T, and R23, and now we have our P3T. So now we just have to plug in all of our information into our Jacobian. So we have H1 is easy. And we have H1 cross. And we're going to have RO1 times P1T. And then we have RO1 times H2. We have RO1 H2 cross times RO2 times P2T. And we'll continue on to the next line. And we have RO2 times H3, RO2, H3 cross, and we have RO3 P3T. So we just took the form that we derived before and plugged in our specific value to get the result we want. And so what we can do is we can look at what the Jacobian tells us for specific configurations. All right, so let's take, for example, our 0 configuration. All right, so Qi are all 0. So we're looking at our Jacobian. Our configuration is 0, represented in the base frame. What's nice about the 0 configuration is in all of our rotations of 0 just makes some identity. So it makes it a little easier to do the math. So we have EZ cross EZ, EX cross EZ, and EZ cross EZ. So there's one big simplification that we can make here. Anytime you have a vector crossed with itself, that becomes 0, right? So if you're trying to do a vector curl towards the same vector, right, you can't really do that. It's a 0 representation. And we have EX. Turns out EX cross EZ is minus EY. And we have EZ, another vector crossed with itself. So what this means, if we go back to our linear and angular velocity, and this would be Q1 dot, Q2 dot, and Q3 dot. Right? So if I wanted to rotate about X, right? So omega captures our rotational velocity. Then what I see is I have an EX here, and that corresponds to joint 2. So we can use Q2 to rotate about X0. If we want to rotate about Z, I could use Q1 and or Q3 to rotate about Z. And for translating, so this also tells me some other things. It tells me that instantaneously, I cannot rotate around the y-axis, and I cannot translate along X or Z. Right? So the Z kind of makes sense that, you know, if I try rotating this joint or this joint, I rotate this one a little bit, instantaneously, I'm not going to get any motion along Z. If I rotate this joint, then it's going to get a little bit of perpendicular motion to that axis of rotation, which corresponds to the y-axis. And rotating either of these joints, I don't get any translational motion. And if I want to do rotation, I rotate either one of these, I'm rotating around the Z. And if I rotate this axis, I'm getting a little bit of rotation around the X axis. And it also tells me when I look at this, that if I only use Q1, I'm only going to get Z rotation. If I start moving Q2, right, I'm gonna get some X rotation and Y translation. Right, so very, very powerful matrix in terms of what we expect our arm to do when we move certain joints. And if we want some certain motion here, there's actually a way that we can do sort of an inverse of this. Not an exact inverse, because if you notice, right? So this is a three column, a 3-row vector, and this is a 3-row vector. So we have a 6x3 matrix. Right? So if you remember from linear algebra review, if it's not a square matrix, you can't do a direct inverse, right? So after the exam, we'll look at some ways that you can approximate an inverse for this Jacobian to figure out what you need to apply on the joints to get some desired motion of your endpoints. Does that make sense? Any questions before we move on to review stuff? Right. So if you go to slido.com, it's going to ask for you to join an existing Slido. You can do it either on your phone or on your laptop, whichever is easier for you. Everybody able to log in? Good. I'll know if I click the next slide and get panic notice. So, first thing, taking the dot product between two vectors. Right, so kind of hard to do math notation in Google Slides. So this vector would look like 1, 2, 4, and this vector would look like 3, 1, 2. And so if at any point you need me to zoom in, I guess I can do that. So just give a holler. Right. So probably that one. Yeah. Let's see. So I thought I had it set up to show the distribution, but I can check that later. So the answer you should have gotten is 13. So one way that you can instantly eliminate 2 is that your dot product, you think of it like a magnitude projection. So your dot product is going to be a number, not a vector. So by that, you can automatically eliminate these first 2 choices. And then for the rest of it, so you take P horizontally, take R vertically, you can fold it over, do a multiplication and summation to get 13. Wrong button. So yeah. All right. So if we take a cross product between two vectors p and r, and the result is m, what can we say about m in relation to vectors p and r? Good. That's definitely good to see. All right, so a way to think about it is x, y, and z axes, right? So those were also formed by taking a cross product. So if you do x cross y, you get z. So you can look at that as a way to get that representation. So let's just say hypothetically that I have two frames. So this A frame is associated with a robot. And let's say they have a B frame, which is associated with some kind of camera. And I'm observing some point Z with my camera. And so what I'm interested in is what is the orientation for this object Z based on my robot frame. But what I can measure is the camera relative, or the point relative to the camera, and the camera relative to the robot. Yeah. Yeah, so what I'm going to do is download the slides, and then in the notes for each slide, I'm going to put the answer. And then those will be posted on Canvas. Each question, we get more people. Interesting. Good. Yeah, so this is a nice thing about our notation, right? So RAB, RBZ, right? So looking at those subscripts, if those middle ones match up, what we would have in the second case is that this would essentially be RBA, right? So then we have trying to convert from the B frame to the A frame, right? There'd have to be some other rotation in there for it to be valid. So similar thing with PAZ. So we have the same information. Now we're looking at what is the position relative to the robot frame A.
What's like the comma?
Transpose. Yeah, MATLAB notation. Because there's not an easy way to do it in using Slido. So. Then we've got critical mass here. Good. So again, with our notation, so PAZ means that we're represented in the A frame. Right, so here we have PAB, so that takes us from point A to point B in the A frame. And then we also need to go from point B to point Z, but this vector is in the B frame, so we need to apply a rotation to get us in the A frame. And so with this one, right, you want this first subscript to match up with the subscript here, right? So that's a good way to double check with the notation that we use. So we have the notation here. This is a Z rotation of angle A, Y rotation of an angle G, so on and so forth. How much can you reduce this down? So when I display the results since you're typing in, it's not going to be a clear cut. So we'll do the explanation here where we can see it. All right, so if we look here, we have the axis EZ, or the vector EZ, and a rotation about the Z axis. Right, so we're rotating about the same axis as the vector is in that direction. So basically it's like this RZ doesn't do anything, so we can just get rid of that. All right, so we eliminate that RZ to start with. And if you look here, we have two rotations about Y. So we can take the angles and combine them inside to be a single rotation. So we have a rotation about Y of G minus G, right? So it'll just cancel out so we have a rotation of 0. So this part just becomes identity. And so what we're left with is RZ of A, RX of B, and EZ. So it looks like we have, like I said, it's kind of messy to see here. All right, so digging back to some of the terminology that we use. A workspace obstacle is the same as a configuration space obstacle. Right, so what an obstacle looks like in reference to the joint angles versus what it looks like for your end effector. Right. The answer is indeed false. And let's take a look at why that is. So here's an example where we have just the two joint arm, where we have alpha and beta are the two joints. And then this obstacle is the circle, right? So in the workspace, this obstacle looks like a circle. But if we look at our angles, right? So this is our alpha angle, and this is our beta angle. We have to see what configurations would result in collision with this obstacle, right? So if you look at all the different configurations that you can have of this arm, it turns out that this weird gray shape is what the obstacle looks like when you're working in your configuration space, right? So you might also have heard of like the piano mover problem, right? So you got something that's a really weird shape that you're trying to maneuver in maybe a cramped space. And so it turns out that trying to plan, so like if I want to move from this point A to this point B, right, that can actually be a pretty difficult problem. And that's where you'll see things like probability roadmaps, rapidly expanding random trees, those type of path planning algorithms to deal with these more complex cases. So we won't get into that in this class. That's something that would be more for robotics too. We'll just look at more free space path planning rather than this more complex space. But the main takeaway is that depending on where you're looking, configuration based versus task based, that these obstacles will look different. So term I've used a lot. What actually is forward kinematics? So it seems like either we've lost some people or some people don't feel like typing today, which is fine as long as you know what it means. So forward kinematics is where we're trying to take our joint angles and figuring out what's going on with the tool or the end effector, that end frame, right? So we're given the joint angles, we're trying to figure out what's going on with the end point. So figuring out both the position and the orientation. And the inverse kinematics is the opposite of that. We're given the pose that we want of our endpoint, and we're back calculating the individual joint angles to achieve that. Oh, well, that sucks. Pretend you didn't see that. And why that? So we're going to Keep for a second here. All right, let's see what happens. Back to. Okay, so I don't know why it's showing it. Considering I've done 3 different ways to hide it. Well, the idea is, given this arm, you want to sketch the arm at a different configuration. So since you can see this configuration, because slides are being stupid, try it for Q being 45, let's say 45, 0, and minus 45. Uh, 45, 0, minus 45. Yeah. So hopefully you've had enough time. Yeah. All right, so terrible joints that angles that I picked to start with, and an even worse sketch. But kind of the idea is that if we look at our original arm here, right? So a positive rotation for this first joint axis would be in this direction. So we're taking it down here to 45 degrees. And since this angle is 0, we're going to maintain that 90-degree difference there, right? So now we have this first joint down here, and then this next part comes over in this direction. And for this one, it's kind of hard to visualize because basically it's just spinning around the end effector, right? So I guess the main thing is that if you were looking at it, it wouldn't look as wide because it'd be at some off angle. So I'm guessing I'll do a quick. Yep. All right, so it's going to do the same thing it did last time and completely ignore all of my appearances. So we're gonna do a little bit more of a challenge one here by having a prismatic joint. And so you won't need to do a prismatic joint for the actual exam, but it's good practice to get the process and to remember what the differences are. So I want you to do the forward kinematics for this arm. So you should specify what the HIs are, what the I minus 1 I are, P, I minus 1 I, and then get the ROT and POT. So, check that out. We need HI, and I should also give you distances. So this distance here, just 1, and this distance here, so that makes sense? Oh, product of exponentials method. Right. Right, although the DH method, I'd be asking you for those alpha, beta. Depending on which DH method. And that is one thing I recommend for your crib sheets is relationships for the DH parameters, both SDH and MDH. Okay, so I did post after one of the lectures kind of a summary page of the two methods. So maybe pulling from that something for your crib sheet. And again, maybe taking a look at the practice exam might be helpful for what kinds of things I might ask about the DH. Just a quick pulse check. How many people are still working? For those of you that are done, if you want to work ahead, the next thing will be computing the Jacobian matrix. And I briefly touched on this when I introduced Jacobian. But if we look at the, let's say the ith column. Figures back a bit. So if you do the Jacobian, that's the main difference between the revolute and prismatic. So the revolute, we get some rotation and potentially some linear as well. With a prismatic, all of the velocity is purely linear. Anyone still working on the forward kinematic? We'll jump back over to slides. All right, so our rotation axes, HI. All right, so our first one is in the direction of Z, our second in the direction of Y, and the third in the direction of X. So we have EZ, EY, EX. Our rotation matrices, right? So the first joint is a revolute joint, and we're rotating about H1, which is EZ. Our second joint is also revolute, and we're rotating around the y-axis. And our third joint is prismatic, so it causes no rotation of the frames on either side. So that rotation is just identity. And because of the way we define these frames, that final rotation is also identity. Looking at the position vectors, right? So we said that this was point 1, 2, and 3. So 0 to 1 is a distance of 1 along EZ. 1, 2, and 3 are in the same position, so these positions are 0. And then since our last joint is a prismatic joint, we have the 0 configuration distance, which is 1 along EX, that EX term. And then we also capture the displacement due to that prismatic joint. So the offset here would be Q3, and that occurs along the axis of translation for that joint. And so if we combine these things together, so ROT, we cascade the individual Ri-1 i's, and we do the simplification because we have a couple identities, and so we just have 2 rotation matrices there. Similarly for POT, right, so we have PO1, and then we can cascade out the rotation with P1, 2, and 3, so on and so forth. And then what's nice is we have a few zeros here that cancel things out, and I have a couple of rotations here that are identities. And so we get this end result once we plug in each of those individual values. Right, so it's pretty similar. You know, we just have this prismatic joint, which changes things a little bit. So it pushes you a little bit outside your comfort zone, but it's good to be aware because you might encounter joints like these when you actually go out and work with robots. Okay, so it turns out when I change my slides, it does not update the same. So we'll continue on and keep those notes set aside because we'll come back and do the Jacobian a little bit later. So subproblems, right? So we had a set of subproblems, and when we were talking about subproblems, we said that each of these is like solving a type of geometric problem, right? So we had one that was the intersection between a cone and a plane, one that was a cone and a sphere, and we had one that was the intersection of 2 cones. So there is a possibility you get a question like this on the exam. So if you can't tell based off of the equations, maybe worth some space on your proof sheet. So it looks like we might have lost some people, but fine. All right, so intersection of 2 cones is subproblem 2. So subproblem 2 is where we had a rotation of some unknown angle of some known vector. right? So we had was back over here for a second, right? So subproblem 2 looks like this, where we have unknown q's on each side. And what we're doing is we're rotating each of these vectors, right? So when we rotate a vector, this forms a cone, and this forms another cone. And we're looking at where those two cones intersect to find this Q1 and Q2. So another thing that I mentioned in class, if we use subproblems to do inverse kinematics, what does that not capture about our arm? So it's looking like maybe a lot of people don't remember what I said about this method. So take a look at those who made a guess. Okay. So if I can there's one. So one of the ones I was looking for is joint limits, right? So the example that I gave in class, if you were to hold out your arm until, you know, the subproblems, I want to take the endpoint down here. It will absolutely give me the solution where I keep these joints the same and just take this joint and rotate it down 90 degrees, right? Not a viable solution for the arm I'm actually working with, but mathematically is perfectly reasonable according to the subproblems method. So that's something when you use this method for inverse kinematics, you always have to go back and check, do these actually make sense? Can I actually use this as a solution? pH parameters. We have 4 of them. What does the D describe? See what people think. Yep, length offset. Right, so theta is your joint angle, alpha is your link twist, A is your length, and then D is your link offset. Right, so the link offset is that distance along the Z axis. So PAB and RAB, what do those actually describe? Good. So from our notation, right? So this is the pose of B relative to A, right? So in this case, we have the position of B relative to the A frame. This is the rotation matrix that would take something that has a B frame, convert it to the A frame. Okay. 10 minutes. So I guess we'll go through this. These will also be posted. So the Jacobian matrix, since we just went over that. So the idea is that each column of our Jacobian matrix has this form, right? This HI cross PIT. So that's true for revolute joints, right? So we're rotating around our HI axis. So that's going to result in angular velocity around that axis. And by consequence, that angular velocity is going to result in some linear velocity as well. And that's what this cross product captures. If you have a prismatic joint, then you're just sliding along an axis. So you're not going to cause any rotation, which is why that first part of that column is 0. And we're only going to have translational velocity along whatever axis it is that we're translating along. And so if we represent that in, say, the base frame, so we need to use our rotation matrices to get the HIs into the appropriate frame. And the same thing with the PITs when we have those as well. Because PIT is in the I frame, and so we use the rotation to bring it back to the base frame. And so for this arm, we have 2 revolute joints. Right, so we have our joint 1 and our joint 2 column, and then we have 1 prismatic joint, which is captured in this way. And so then from where we did the forward kinematics, we had our HIs and our RI-1Is, so we can plug those in down here. And then we can compute the PITs. Right? So the way that we had it defined, this was P1, 2, 3, right? And so we have P1, 2 was 0, right? And then we have P2, 3, P3T, right? So we can capture all of that into our PIT. And then if we wanted to look at it for a specific configuration, such as the 0 configuration, right? So all these rotations come out to 0. And this Q3 is also 0. And so we would get something like this, which tells us that we can use joint 1. That's going to give us Z rotation and a little bit of Y translation. If we use joint 2, we're going to get Y rotation and negative Z translation. And if we use joint 3, we're going to get pure Z, or pure X, translation. Right? So the main thing with when we're computing the Jacobians is basically to remember the form of the Jacobian and plug in your values appropriately. And then if you want to do it for a specific configuration, then you can plug in your Q values into your Jacobian matrix. All right. Right-hand rule, Z cross X. And it is Y. Right, so if you have trouble visualizing, you can sketch X, Y on your paper, and then know that if you have X cross Y gives you Z, so that gives you your axis to start with. And if you put your fingers in the direction of Z and you curl towards X, you find that your thumb is pointing in the direction of Y. And I'll try to remember to bring in little magnets for those that have a little bit harder time visualizing. Then you can have something kind of put on your desk to help with that during the exam. So this one's a kind of fill in the blank. We're getting kind of close to time. So the advantage of a quaternion to represent the orientation over something like a rotation matrix. So we'll talk about this more after the exam. But the big thing is that the quaternion is a rotation representation which does not have singularity, right? So if you think about the idea of gimbal lock, the reason that that occurs is because of the representation of the orientation, right? So it's a product of using the Euler angles. And it turns out when you use quaternions, you don't have that problem. And another thing is that quaternions are much easier to interpolate, right? So we talked about this idea of the slope. So that's a way that you can interpolate between quaternions to get your, if you want something like a linear change in your rotation. So there's just a few other things. So redundant arms have more degrees of freedom than in the space that they're working in. So this is just another checking to see sizes. So I will upload these so you can verify those as well. Degrees of freedom in an arm, 7 degrees of freedom, 3 shoulder, 1 elbow, 3 wrist. You have some very fast responders. Okay. Why we did that camera. So we'll also be talking about this after the exam. So the idea, if you want to interact with an object in your space, that you would use, that maybe you can only measure based on the camera. So you'd have to have some way of figuring out where the object is relative to you based on information from the camera. And somebody's having fun. So the Python package is SciPy. So that's where you're going to find a lot of your rotations. And then I just have a couple of fun ones. So this one I'd be interested in the answer to for those that are still on, just out of my own curiosity. Then also what you'll see in the slides is there's a list of some major companies that build robots. Some of them you've probably heard of, some of them maybe not so much. So gives you kind of a starting point if you're interested in doing more with robotics in the future. And also just a couple of cool examples that I found of some robots that exist. So what I did last year we did an in-class practice exam. So like what was posted instead of review slides. So I'd be interested to get feedback, what you found might be more useful actually doing an in-class practice versus review slides. So anybody who has an opinion.
There's into the yeah, okay. I haven't got a chance to look at it yet.